Okay, recall. A is e to the natural log of a. Normally we go this way, but you could also go this way, meaning a raised to the log base a of x is x. So if I want to go in this direction, I could. If I look at this problem, and I'm looking at the limit as x approaches infinity, x is going to be raised to the infinity, and 1 over infinity is 0. So this we use for 1 to the infinity, 0 to the 0, 0 to the infinity, and infinity to the 0. Whenever you're dealing with a power and you want to move power down, you're going to use logs. So what we say this is the limit as x approaches infinity of e to the natural log of x to the 1 over natural log of x. Kind of odd to see too many logs, but if you think about it, if we take that as a power, the base of this log and the base of this exponential match, they undo each other, and you're left with this. And now what we say, this is the limit as x approaches infinity of e to the limit as x approaches infinity of x to the 1 over natural log of x. Natural log. And one of the properties of logs, I could move this up front, and I'm looking at the limit as x approaches infinity, and that would be e to the limit as x approaches infinity of 1 over natural log of x, natural log of x. Now I have two options. I could think of that as 1 over natural log of x times natural log of x, or I could think of that as natural log of x over natural log of x. Either or. So when I'm looking at those, I notice that those undo each other, right? And that would be the limit as x approaches infinity of e, and the limit of the constant is the constant, and that would be just e to the 1. It doesn't always work out this way. This one did. Here's another problem. Looks could be deceiving. Do not think that's the same thing, but that's the same idea. This is 1. 1 over 0 is infinity. 1 to the infinity, another one of those. I'm going to write this as the limit as x approaches 1 from the right of e to the x, e to the natural log of x raised to the 1 over x minus 1. And that's going to be the limit as x approaches 1 from the right. What properties of logs, I could move that up front. And the same deal happens. I can think of this as natural log of x times 1 over x minus 1. I could think of that as natural log of x over x minus 1. As x approaches 1, if x is approaching 1, I'm getting a 0 over 0. So it seems if I stretch that, that fits me better. Because if I put it here, that's going to be 1 over 0, which is infinity times 0. Then I have to manipulate it. There it is manipulated. Every time I should consider doing this. And this would be 0 over 0 by L'Hopital. That's the limit as x approaches 1 from the right of e. Derivative of the top is 1 over x. Derivative of the bottom is a 1. I need to make that a bit bigger. There. And as x approaches 1, that would be e. You throw 1 in there, you get a 1, and there it is. And next problem up is number 58. And pretty much, if I take the limit as x approaches 0, I notice e to the 0 is 1, and 1 over 0 is infinity. The same problem happened. This is going to be the limit as x approaches 0. E to the natural log of e to the x plus x raised to the 1 over x. Properties of logs, I could move that up front. That's the limit as x approaches 0 of e. And again, should I write it as natural log of e to the x plus x times 1 over x, or should I write it as natural log of e to the x plus x over x? As x approaches 0, if I write it this way, the 0 in the denominator, That is a 0, that's a 1, and that's a 0. Natural log of 1 is 0, so it seems it fits me better to simply straight out write it this way. And now I could show that the power, I don't need that. I could show the power is 0 over 0. So by L'Hopital, that's the limit as x approaches 0, e. Derivative of the denominator is 1. Derivative of the top is 1 over e to the x plus x times e to the x plus 1. This is the limit as x approaches, as x approaches 0 of e to the x plus 1 over e to the x plus x. That is, that does it. That is e to the 2 over 1, which is e squared. Very good. There it is. A few more examples to go. And if I look at this, the limit as x approaches infinity, that's infinity raised to the 0 power, the same deal. That is the limit as x approaches infinity of e to the natural log of x squared plus 1 over x plus 2 raised to the 1 over x. Properties of logs, I can move that forward. And it's no big secret, I'm going to need to really make that and let me see if that works. As x approaches infinity, that's going to approach infinity, and natural log of that is infinity over infinity. Very good. And I'm going to apply L'Hopital, but it's going to be a bit messier than the traditional. I'm going to write an extra step. There we go. Much better. So we can see what's going on. And here's infinity over infinity. And by L'Hopital, that's e to the limit as x approaches infinity. The denominator is 1. Derivative of a log is 1 over the argument. Times the derivative of the top. All over the bottom squared. Thinking if there was a better way of doing this. That would be the limit. That would be e to the limit as x approaches infinity. And let me see how that works. That is x plus 2 over x squared plus 1. And the top will be 2x squared plus 4x minus x squared minus 1 over x plus 2 squared. That would be e to the limit as x approaches infinity. This cancels one of those. And that would be 2x squared plus 4x. That would be x squared plus 4x minus 1 over x squared plus 1 times x plus 2. You could FOIL this if you want. Distribute a FOIL. You could FOIL the bottom. Or you could say, you know what? I'm going to divide by the highest power term of the denominator, which is what I advise you to do. So you divide the denominator by x squared and by x. That makes this 1 plus 1 over x squared. And that's 1 plus 2 over x. That means you divided the denominator by x cubed. You divide the top by x cubed. 1 over x plus 4 over x squared minus 1 over x cubed. That's a 0, 0, 0, 0, and 0. That is e to the 0 over 1, which is e to the 0, and that turns out to be 1. Last problem I want to look at is number 66. This is a 0 times, and that's infinity, negative infinity. So again, need to manipulate, and by now we know Whether I'm integrating or taking a limit, logs we don't touch. And that would be infinity over infinity. By L'Hopital, that's the limit as x approaches 0 from the right, 1 over x. And derivative of negative cosecant is negative cosecant of x cotan of x. Let me fix that cotan of x right there. So derivative of cosecant is negative cosecant of x cotan of x. That's the limit as x approaches 0 from the right. And what would that be? This will move to the bottom, so that is negative x, and that will be sine of x tan of x. So that's 0 over 0 again. I'll apply L'Hopital one more time. X up. That would be by L'Hopital, the limit as x approaches 0 from the right, negative. The denominator is 1. The top is cosine of x times tan of x plus sine of x times secant squared of x. And if I put a 0 in there, that's a 0, and that's a 0. I'll get 0 over 1, which is a 0. There's the rest of the homework for this section. And that concludes 4.5 review.